Hi and welcome. I'm trying to learn particle physics. Today quarks, and after we've done it, we're gonna do stretching. And if you participate in the stretching, then it's at your own risk. This is part 7, 8 of quarks. The same way that meteorologists and climate scientists attempt to simulate the swirling complexities of Earth's atmosphere by reducing it to a three-dimensional grid of points spaced kilometers apart, lattice quantum chromodynamics reduces a nucleon's interior to a lattice of points in a simulated space-time tens of femtometers across. Okay, we're saying the people who are measuring the weather, making a model of it, and now also the people who are trying to understand how atoms work and the nucleus of the atom, also making a big model of it. Quarks sit at the vertices of this lattice. I don't know what vertices are. While gluons propagate along the edges. Maybe are they always at the cornerstones, at the cross points? That means the vertices. So it's different places, and the gluons, they are propagating along the edges. They're going somewhere along the edges. By summing up the interactions along all the edges and seeing how they evolve stepwise in time, you begin to build up a picture of how the nucleon works as a whole. So we're just looking where the gluons going, whatever. Trouble is, now the new part. Even with a modest number of lattice, trouble is, even with a modest number of lattice points, say 100 by 100 by 100, so we're having 100 down and 100 to the side, and then also 100 up front. With these 100 lattice points, separated by 1/10 of a femtometer, that is an awful lot of interactions, and lattice quantum chromodynamic simulations require a screaming amount of computer power. Okay, the computer have to calculate a lot to calculate these 100 lattices, so it was by a million or something in total, of different lattices and where all these things of the nucleus could be and how they're interacting with the gluons. Complicating these things still further, because quantum physics offers no certain outcomes, these simulations must be run thousands of times to arrive at an average answer. So just to make the simulation how an atom works with these lattices where all the atoms are, one time doesn't work, we have to do it multiple times because it works every time differently. To work out where the proton and neutron masses come from, Fodor and his colleagues had to harness 2 IBM Blue Gene supercomputer and 2 suites of cluster computing processors. Harness seems to mean something like to get. I don't know what harness means. Whatever, they needed a lot of computer power. In 2008, they finally arrived at a mass for both nucleons at 936 megaelectrovolt. Give or take 25 megaelectrovolt, pretty much on the nose. They came out with 939 megaelectrovolt, which is very, very little in mass at all. But it is what the mass is. This confirmed that the interaction energies of quarks and gluons make up the lion's share of the mass of stuff as we know it. The lion's share of the mass of stuff as we know it. The quarks are doing a lot there of the energy, which is where I don't get it. You might feel solid, but in fact you are 99% gluon interaction. But that's what I mean. 90%, but we're saying human body or an object is not solid as one thing, the atoms are, but the most 99% of the energy are the gluons running from one thing to another thing. But the calculations were somewhere near precise enough to pin down that all-important difference between the proton and neutron masses, which was still 40 times smaller than the uncertainty in the result. But the calculations were nowhere near precise enough. So the calculations weren't precise enough to pin down that all-important difference between the proton and neutron mass. Okay, the proton and neutron, they have different mass. The neutron is 0.1% heavier than the proton. And that is important. They have it in the previous one. In the sun, or basically in the sun or something else, if mass would be more similar, then chemical elements would just appear as new thing. But because there's a difference, they cannot just appear. A chemical element cannot become just another one because of its proton-neutron mass, something like that. They say if it would be smaller, other elements would just spontaneously happen and no universe would exist in the same way as it does now. And if the difference would be bigger, then a nuclear fusion or whatever happens in the sun wouldn't be able to make a new chemical element, and it would exist just hydrogen and helium. So it is important that the difference between the mass of protons and neutrons is by pretty exactly 0.1% to make it able that in a burning sun a new chemical element is created, but not so high that it happens not at all, and not so low that it happens spontaneously. And now this calculations that we done with these 2008 with these supercomputers of the grid which we did weren't enough to find out where precise which was now when you have to pin down with to find out why or whatever the difference y is, which was still 40 times smaller than the uncertainty in the result. Yes, they weren't precise enough. The uncertainty was 50 times bigger than the difference of 0.1% of the proton-neutron mass. So they were not precise enough to measure in a difference of 0.1% difference. What's more, the calculation suffered from a glaring omission. I don't know what an omission is. The effects of electrical charge, which is another source of energy and therefore mass. We did the experiment wrong. We had electrical mass in it, and this is what I get from it. I don't get it. This is what I get from it. I'm not sure if it's true. They used electricity to run the experiment, and that had an influence on the outcome. Let's do it again. What's more, the calculation suffered from a glaring omission. The effects of electrical charge, which is another source of energy and therefore mass. No, I don't say through the experiment. The effects of electrical charge, whatever, there was electricity at work. Maybe it was already there, and it was not that you did the experiment wrong. All the transient quarks and anti-quarks inside the nucleon are electrically charged. So but it's not that you did the experiment wrong. It is that the quarks and anti-quarks inside the nucleon are electrically charged, giving them a self-energy that makes an additional contribution to the mass. So all these quarks and anti-quarks, and don't forget the difference. They are gluons, they are quarks, they are protons and neutrons, and these neutrons and protons exist out of quarks. And they have energy, and that changes something at their mass, and now to measure their mass is difficult because they have energy. Without taking into account this effect, I totally forgot what to do in fitness in a moment. I think it's touchy. Without taking into account this effect, all bets about quark masses are off. I don't get what it means. The bets are off. Does that mean everyone is betting, or does it mean no one can bet anymore? The bets are off, so the way of let's go, and the way off the table. You can't bet anymore. But yeah, talk about one compound particle being more massive than another because of difference in quark mass is a crude caricature. I don't get the part. Says Wilczek, who won a share of the Nobel Prize in 2004 for his part in developing quantum chromodynamics. Okay, he said, talk about one component particle being more massive than another one because of the difference in quark masses is a crude caricature. I don't get it. It's a thing with a bit off. Does it not mean it is a crude caricature? It is not crude. Or does it mean I don't get it. The subtle roots of the proton-neutron mass difference lie in solving not just the equations of quantum chromodynamics, but also quantum electrodynamics, which governs electromagnetic interactions. So we had to understand the quantum chromodynamics, we had to understand quantum electrodynamics. I think because when we understood the quantum electrodynamics, we understand the self-energy and the energy which the quarks and this other stuff had. So we could take that away and could measure exactly what is now the exact mass without the energy. So first we had to solve the quantum electrodynamics. That is a theorist's worst nightmare. It's awfully difficult to have quantum electrodynamics and quantum chromodynamics in the same framework, says Fodor. So to calculate two things at the same time is more difficult, basically. The electromagnetic self-energy can't even be calculated directly. Okay, we cannot calculate the electromagnetic energy. In a limited lattice simulation, its interactions create an infinity. Oh? Because we're forever going on this gluons where's infinite energy. Because we're going from where, this is plus one energy, back, plus one energy, and back, and back, and back. And we can't calculate it because it goes over and over and over again, higher and higher. Okay. In a limited lattice simulation, its interactions create an infinity, a mathematical effect rather like a never-ending reverberation inside a field. Why is there no mathematical effect? Rather than a reverberation effect inside of a field. By saying it gets higher and higher and higher, and it's the same as it goes plus one, plus one, plus one, and not the way an echo comes back and forth, but an echo gets longer. Whatever. Working around that took time. But in 2015, Fodor and his team eventually got there, coming up with a value in agreement with a measured value or with an error about and again and maybe speaking about words. Working around that took time, but in 2015, Fodor and his team eventually got there, coming up with a value in agreement with a measured value. With a value in agreement with a measured. They could agree on a number, although with an error of about 20%. So they agreed on a number. What we quantum electrodynamics is, they were a bit wrong, but they were pretty much there. You might be forgiven for wondering what we gain by calculating from first principles numbers we already knew. No, but okay. You might be forgiven for wondering. I'm not wondering. Not forgiven. I'm not wondering. You might be forgiven for wondering what we gain by calculating from first principles numbers we already knew. So by calculating numbers which you already knew. Okay. But quite apart from this particular number's existential interest, many physicists are looking far into the future. Just as we invented new technologies and found new sources of energy by fully understanding the electromagnetic force way down the line, something similar might be possible if we can fully get to grips with a strong force and the workings of the particles it manipulates. Then it would be a case of welcome to the quark ages. Whatever, being able to calculate it properly gives more possibilities. That was the particle physics part. If you go here for particle physics, you can go directly to the next part of particle physics. If you stay and participate in the stretching, we have 3 minutes, and that's it, yeah, let's go. We are standing on this level, short of the part, every breathing, and that's the answer. And before we go to the side. In. And out. In. Out and down, breathe in. Out one hand slides down the leg, the other shoulder stays down. Breathe in. Out the arm. Breathe in out the rib cage. Out and back. Breathe in. Out one hand slides down the leg, the other shoulder stays down. Again in. Out one arm. Breathe in. Out back. Have feet standing together, breathe in, lift the arms up. Out one arm down. Breathe in the feet. Out arm up. Again in. Out arm down. Breathe in, reach. Out arm up and down. Leg shoulder wide apart. Everything shoulder circles. Back. Front and leg down. Again back. Front and down and in front. Down and down and front. Down. Breathe in the shoulders up. Out and down. In up. Out down. In arms up. And reach high. Pretend to take an apple leg. Eye on an apple branch. The time is bitter down. And then switch it out. And over to the shifter. Arms up to a T. Breathe in. Out over to the side. In. Out. Again in. And under the knees leaning, below the buffalo doing it. The buffalo fighting its hangover. Breathe in. And over and shoulder in front. In back. Out the other one in front. In and back. Out in front. In back. Out in front. In and back. Out, hang down in the other forwards. Breathe in. Out over to one leg. Breathe in. Out over to the other leg. Breathe in. Out into the middle. Close the legs with the Angelo. Breathe in. And out. Again in. And out comes longer with the round back up, back at the top, up backwards, shoulder away. Next one apart, breathe again down. And breathe again out. Take it in. Hold it. Breathe in and close the legs. And breathe again out. That was for stretching. Thank you very much, and next time.